We're the Arctic Sea Ice group.
I'm Maddie.
Maddie.
I'm Jose.
I'm Ryan.
I'm Nicole.
I'm Jesse.
I'm Yasmin.
And our helpers were Christian and Paul.
So I guess we'll start with explaining what me and Jesse primarily worked on. So we wanted to focus primarily on melt ponds and ice breakage and how that affects albedo, and then later on how we can use that to see how energy affects albedo, energy of the ice. So we showed this picture before, but again, it's a picture that shows that the surface area of the Arctic has drastically lessened over the past 30-ish years, and it only keeps getting worse. And our ultimate goal is to measure at what rate is it depleting, and can we predict the year when it'll be gone, or if during the summer it'll be gone and during the winter it'll come back. So cool. We had two data sets, melt pond formation in June and the proportion of ice melt ponds in seawater in 4 Arctic sites. For the first data set, we used it to try to get an average for the depth of the melt ponds in the Arctic, because the depth of the melt ponds matter when measuring the albedo, because ice and open water have a set albedo, while melt ponds change in length, though it ranged from anywhere from 0.2 to 0.65 in albedo. And the second data set we used to try to get make a time series of the albedo of the surface area over time, over the summer months. So, what did I do? Oh, there we go. Okay, so this was the Arctic Sea Ice melt statistics and map. We got about 100 of these pictures, and they were analyzed with supervised maximum likelihood classification. And from each picture, we got a percentage of area covered by pond, percentage of area covered by ice, and then covered by open water. And open water included the ice breakage. And then our data came from 4 sites measured over 3 years between 1999 and 2001. So this was our first map we made. We calculated the albedo of each picture, and for all the 3 years, and we wanted to see, is there a certain, so let me back up. Our original hypothesis was that melt ponds will start forming sometime around early June, late July, and they'll drain late July or early August. And when they drain, the albedo of the surface should go up, because when they drain, more ice is exposed, and therefore there's an overall higher albedo of the surface. However, from this we couldn't really tell much, because we can see that the albedo of the surface starts way up there and then kind of goes down, but we couldn't see if it actually goes up. But what we realized is that there was a lot of missing data here, so we made a plot removing all the missing data. And as you can see, early July the albedo starts around 1.8. It goes down, and then starting August, it ticks up a little bit and then goes back down in September whenever the ice, I guess, fully melts. And then these pictures correspond to the time. So the cyan, I don't know if you can see it very well, is the melt ponds. The white is the ice, and then the blue is the water. So here there's a lot of cyan, which means there's melt ponds are starting to form. Here, whenever the albedo starts picking back up, the cyan is mostly gone, which means they drained. And then over here, there's a lot of open water, which makes sense, because when there's a lot of open water, the albedo will spike down a lot, which is what happened here.
So in the Eisenmann Wetlaufer paper, which is what we used, the way they measure albedo is a function of energy. And the parameters are the overall albedo in a picture is the albedo of the mixed layer, which is ice and water, plus the albedo of ice, plus the albedo of mixed layer, subtract the albedo of ice over 2 times the hyperbolic tan function. And there's energy, and this is a smoothing constant on the bottom, based on, that's a rough proxy for the thickness of the ice. So what Jose and we had measurements and sparse data points for this, and we were able to back out measurements for the albedo. And so what we did was, this is how we measured out the albedo on the bottom and the energy on the top. And so to add in, because the data was so sparse and we had the element of uncertainty in our measurements, and so we added in a stochastic component to model out the different situations. We made some rough assumptions here, but we had the depth of the melt ponds from the data, and we had a mean standard deviation. And so we generated 100 different simulations from a Gaussian distribution and sampled those to get our energy values. Then we got our albedo values by generating uniform sampling from a uniform distribution on the albedo of the melt ponds. And the rest of these parameters are known from the papers or from what we researched. And so here's the results of 40 samples that we took from 100 different generations of those stochastic variables. As you can see in the middle there, at around negative 20 joules of energy, this is when melt ponds begin to form. And there's a greater element of uncertainty in that area as these melt ponds form and then drain. So there's different paths that can happen. The albedo can increase as the melt ponds drain out, which results in more reflection, or the paths where the albedo decreases more significantly as the melt ponds continue to get deeper and absorbs more light from the sun. So from this stochastic output, we estimated some parameters to go into the model on how the different functions, the dynamic model of climate of the ice. And so from our first presentation, we had the hysteresis curve. What this is showing here is that the hysteresis basically happens at an earlier stage after we factored in the drainage of the melt ponds and the ice cracks that formed right around here. That wasn't accounted for before in the Eisenmann and Wetlaufer model. And so it's hard to see here, but in the original model, there were only 4 sample states that resulted in a totally ice-free Arctic. After we factored in the ice cracks and the melt pond drainage, and fitting it to the empirical data, we realized 7 different states where the Arctic can be ice-free.
So while they looked towards statistical analysis, I was focusing more on the modeling part. So what happened is, as energy increases, this equation changes the albedo, and as we had this picture in the earlier slide, but as the energy goes up, this ice becomes permeable and the melt ponds start to drain, as well as large cracks form in the ice, and that's how they all drain out. So the goal was to model this process and get a better estimate of what that would do to the equations that we were already looking at. So this orange line is the original albedo model, the one that they use. This hyperbolic tangent does some major smoothing. So by creating these other equations, changing the albedo and putting that into the same statistical analysis we used XPP for, we could kind of see what modeling these changes might do. So this is the original equation. And then to change it, I basically looked at this temperature range that was in the paper we primarily used that changed the rate of drainage. And what I did was I added a Heaviside function to create a piecewise function that would look like these models. So by varying f of t, we can make these different loops, and by varying these numbers, we can change how long they affect the albedo. So these were the models that we used. As you can see here, we had a linear f of t, and it didn't look very different than the original curve at all. And then these other 2 curves are a little bit more drastic, but if you look closely at the axes, these are only affecting the albedo within that critical temperature range that the paper found. In reality, we would expect it to affect the albedo over a longer period of time, because as it increases it here, it changes how it reacts in here. So those were the 2 longer lasting models, and we would expect it to behave more like that. So we ran XPP for all of these, and we didn't see that much change. All of these smaller bumps had this exact same graph, but the longer lasting effects, it's very hard to see. They have one less equilibrium state down here. And this is over a range of different fluxes for the surface temperature. So basically, the larger bumps would just have one more equilibrium state that is up above freezing. And then we wanted to see the bifurcation as well. We wanted to see if it persisted, but since we were creating a piecewise function, it's not continuously differentiable. However, by coming at it from two different initial conditions, we were able to get half of the model on either side. So we can see that the bifurcation does persist, we just couldn't get it on one continuous graph. And then another thing we really wanted to do was look at some graphical analysis of the equilibrium states. So this is the energy equation that we used. This is the albedo that we got from this equation. And so equilibrium states are just when this change in energy term is 0. So by graphing this term and the rest of it, we can see where they intersect based on different fluxes, which is this term. So with no change in flux, we have one equilibrium state all the way down here. However, as the flux increases, the line will move down and intersect with the line at multiple different points. So the interesting thing about the melt pond drainage is that it creates this bump in the graph that you can kind of see here, just right there. And this just creates extra equilibrium states whenever the flux is within that range. So for instance here, there are 3 extra equilibrium points that are created, as well as the 2 on either far side. So with the original model, with no flux, there's only one equilibrium state, and it's stable. By evaluating the first derivative of these equations, we could evaluate their stability and see what's going on. So when there's 2 points, one is unstable up here, and this point remains stable. When there are 3, which would be a standard, this kind of model, we have one steady state up here, one down here, and an unstable point in the middle. And then when there are 4, for instance, when it's just touching that point, there are 2 unstable states in the middle and these 2 stable ones on the outside. However, when we get this state, where there are 3 extra equilibrium points, the one in the middle is a separate steady state that isn't included in the original model, without the bump. So whenever we're within this range, this interesting new dynamic is created. So to do that, to evaluate that, we looked at a range of models in this area. So this is just varying flux. And by varying the flux here, we were able to see that they have different equilibrium states. It changes the steady state solution that the system will end up at.
Okay, so with the constant average solar energy input, based on this different equation, f of x represents the energy coming from space, from the sun. F of O is represents and f of t represents the energy going to space, and this here represents energy that's staying in the layer of Earth. And what we did was we wanted to have a smoother graph, so we simplified this to this model here by using. We also have to use the Fourier series, which is this formula here, and these here, A of them represents, and A of them and B of them are the coefficients in the Fourier series. And what we did was we used that formula to plug in our we used the Fourier series to plug in for our the energy coming from in space, out of space, and within the Earth to get a more accurate graph in XPP. And you see here.
So we changed 3 different parts of the simplified model: the temperature-dependent surface flux, temperature-independent surface flux, and the solar radiation flux. So the temperature-dependent surface flux represents the opaqueness of the sky, so more clouds will trap in more heat. And then we have the temperature-independent surface flux, which is the cloud cover and also the heat that comes from lower latitudes. So the heat from the south will move up towards the Arctic, the colder it is. And then we have the incident shortwave radiation, which is just the solar radiation in the Arctic, and it's going to be 0 at some points here because it's completely dark in the winter. So our original model used the yearly averages to represent the amount of ice and CO2. And in our new model, we have a periodic orbit. Everything below 0 has ice. Everything above 0, there's no ice. And then if you look here, there's a line that went from below 0, so it's going to have ice. And then above 0, it's not going to have ice. But as it rotates around the 0 axis right here, that means that there's ice in the winter and then no ice in the summer.
Some future goals we have for the seasonal group. The F0 equation takes into account southern latitude temperatures, and those original measurements were taken between 1970 and like 2000. And so what we want to do for the future is update those values with newer temperatures as like the climate gets warmer, so to make a more accurate model. Also, wait, is this?
Secondly, we would also like to investigate how the warmer climate might affect the cloud cover in the Arctic. A lot of the satellite images that we had didn't account for a lot of the cloud cover. There's a lot of empty spaces in the grids. And finally, we'd like to optimize albedo parameters for more accurate model inputs. So all that stochasticity, reduce the uncertainty in that respect. Thank you.
Any questions?
I might have missed it, but how do you account for the missing data? Did you say you did some means or labor?
So for the missing data, we ended up removing it.
Sorry?
We ended up removing the ones that had missing values in them because there was no real way to
Like
predict.
the mean or anything?
So the part that was missing was the percentage of pond coverage and percentage. Oh, yeah. It was percentage of pond coverage and percentage of open water coverage. The data gave us percentage of water, which was the pond and open water combined. So we couldn't really, what we did originally was like divide them in half, the percentage of water, into open water and pond. But we thought that was wrong because there could be 1% open water, like 99% pond.
Yeah.
So we ended up removing it, but we saw that it still looked good, and it looked even better than with all the missing data, all the points in the graph. So, and that's why we did the 100 simulation, and we sampled 40 to create a spaghetti plot. Yeah.
Basically, data that didn't delineate between ponds and water was thrown out. So we only the ones that could tell us with how much pond, how much was the water.
Okay.
So it was just a
So
matter
there was
of
nothing
right.
in the mistake of the
Right, yeah. Right, there just wasn't enough information for those particular points.
Do you have a question?
Yeah, so what did you do to make sure that your calculations and results were accurate? Like, did you do any correlation or any checking?
Or for us, or?
Yeah.
In specifically, like in this equation, these equations?
Or like when you made your plots and charts and you showed patterns, how did you make sure that those are actually accurate?
So we had two moving parts in this thing. Essentially, Maddie was working on a very similar part that we were doing. However, we were working with the actual data to sort of verify what she was doing was correct. And it just so happened that we ended up getting very similar looking charts. So she ended up modeling that little bump that account for the melt ponds. When we looked at the empirical data, we ended up getting something very, very similar. So that was like a big green light for that what we're doing was sort of in the right direction. It's observable, and in theory it works. So that was a way to measure. In terms of how we ended up getting these equations, we use a lot of wild assumptions. We assume like taking uniform draws. We're assuming that the depth of the melt ponds is Gaussianly distributed. We didn't do too much like in-depth statistical analysis to see if that's correct. And a lot of these were rough estimates or taken from research.
Yeah, for example, this one we got a mean of the melt ponds from the first data set we analyzed. And then this one was, we looked at a lot of papers and saw that it varies between 0.25 and 0.6.
Maybe like you want to check on your terms next time?
Oh yeah, for sure. We would
Yeah.
want to get like a better estimate of what the albedo of melt ponds are, because we know that as like the height of the melt ponds increase as the summer goes on, but at some point they drain, so they all go away and they come back. But we couldn't really have enough data. We didn't have enough data to model that relationship.
Anything? Yeah?
It's not a question, it's more like what Maddie was explaining, which, can you go to one of those graphs where the range was like overshooting and the other one was just touching at equilibrium?
Sorry.
We cannot.
Never mind, I'll ask you later.
Cool. Any questions for the team?
Sorry. Should be able to.
Yeah?
Just had like one question about the equation was said that the F naught and the FT were both like outgoing long wave radiation. But what's the difference between
I
one and the other?
think that was what my question was. Do you mean like where it was going like overshooting and the other one was just touching that?
No.
Just to explain real quick, it might be, I think F and T would just due to like to say like it might be clouds interfering versus like, you know, like just say no clouds in there because that area, the Antarctic is the Arctic, it has like during like a certain seasonal time, just like, you know, for 6 months it's no sun and 6 months it is sun, so that's what kind of, well, at least from my understanding, this is my first time learning how to do, using the Fourier series. This is actually my first actually like playing with it, and that was my assumption. So yeah, that's the best way I could answer as of now. I'm really new to this, but I think from my assumption was, you know, due to like we looked at each month, like I know like half the years, like I said, is dark, half the year is sunlight, but even during the 6 months with sunlight, it still might be clouds. So it just, you know, based on that. Yeah. And one thing too, like you know, the greenhouse effect does have a lot of involved with that as well. That's why some of the energy would stay in the Earth. That's why like a long time ago, actually, Earth was actually like they call it the snowball Earth, where it was no like really any oxygen really, so like the whole world was frozen until like, you know, volcanoes had to like keep erupting so for so many X amount of million years. So that's what I just know for now.
Okay, what was your question?
Yeah, I think it describes it.
Awesome.
We should, let's thank the group.